Hello, my name is Ian Dickinson. So this is for the P2 point creating 1.1 gigabyte for the end-to-end delay of sending one packet of length L over N length to Christian weight. Point all to this formula for sending P sub packages back to back over N length. The following in the scenario applying the formula of the end-to-end delay, which is the end-to-end equal N L flat 4, L in the length, N in the length, R in the weight, and P in the package. So we can only have one packet or each length at a time. At T equal NL plus R, the fourth package reaches the destination at T equals NL divided by R plus L divided by R. The second packet reaches the destination at T equals NL divided by R plus L divided by R plus L divided by R. The third packet reaches its destination at T equals NL divided by R plus P minus 1 divided L divided by R. The last packet reaches destination, and this is head of relation. We put them all together. T equal to NL divided by R plus P1 minus P minus 1 L divided by R equal to N plus N minus 1 L divided by R. So the answer is L divided by R 1, L divided by R 2. P3. Consider an application with transition data at the state wait, for example, the standard generator and N length of data K unit where K is small and fit. Also, when such an application starts, it will continue running for a relatively long period of time. Answer the following question briefly. Justify your answer. Would a packet switch network or circuit switch network be more appropriate, and why? Suppose that a packet switch network is used and the only traffic in this network comes from the application as described above. For the assumption that the sum of the application data is then captured, each link is a form of distributed control needed, and why. For a circuit switch network would be very well suited for the application described because the application involves large sets with pre with predictable smooth bandwidth requirements, since the transition rate is well known and not and robust bandwidth can be resolved for each application session socket with no significant waste in application. We need not to worry about greatly about the overhead cost of setting up the tearing down a circuit with or makes it over the length duration of a typical application session. Given the general length cable, the network needs no congestion control mechanism in the world, mostly potential congestion in case of all the applications related transition over one or more practical network link. However, since each link offers significant bandwidth to handle the sum of all application data, no no congestion, very little queuing rarely occurs. P4. Consider the circuit switch network in figure 1.13. Recall that there are four circuits on each link, labeled the switches A, B, C, and D, going in the clockwise direction. A. What is the maximum number of situated congestion that can be in process at any one time in this situation? Suppose that or connection between switches A and C. What is, I made a mistake. What is the maximum number of synchronization connections that can be processed? And C, suppose we want to make 4 connections between switch A and C, and another 4 connections between switches B and D. Can we route the code through the 4th link to accomplish all 8 connections? Now for A, between the switches in the upper left and the switches in the upper right, we can have 4 connections. Similarly, we can have 4 connections between each of the 3 other pair adjustable switches. Thus, this network can support up to 16 connections. B, we can have 4 connections pass through the switch in the upper right hand corner, and another 4 connections pass through the lower left-hand corner, giving a total of 8 connections. C. Yes, for the connection between A and C, we can route 2 connections to B and 2 connections to D. For connection B and D, we route 2 connections to A, 2 connections to C. In this manner, there are at most 4 connections passing through any link. This was a little difficult for me. P said this elementary problem begins to explore the progress delay and trigger delay, 2 certain connections in the data network. Consider 2 hosts A and B considered by a single link or BPS. Suppose that the 2 hosts are separated by m meters, and suppose the progress speed along the link is s meters per second. Host A to send packet L bit hosted by B. A. Express the progress delay a D prop in the term of M and S. D prop equal to M divided by S. The progress delay is determined from the distance traveled in meter distance by how fast the data travels in terms of meter per second. B. Determine the expected time of the packet dtrans in terms of L and R. And here's go over here. Dtrans equals to L divided by R. L a bit, R also a bit. Transmission delay and how long it will take to get all of the data onto the network. C. Ignore the pocket and QA delay optimized especially for the end-to-end delay. Dn equal to dpart and plus dtrans. End-to-end delay is when you take all possible forms of delay the data will experience and add them up to a single number without including process and queuing delay. The answer is just to add the pocket delay plus transition delays. Almost gets D. Suppose a host A begins transmitting the packet at time t0. At time t, dtrans. When in the last bit of the packet, just let A sit. The bit need to be on the link before transmit can start. The link last bit of the packet will have immediately just left the host. E. Suppose that dpart is greater than dtrans at ttrans, where the 4-bit package between host A and B. Dtrans means the packets are now on the link, but because dpart is greater, it still makes time to get host B. Therefore, the packet will be between the 2 links. To fall. Suppose dpart is less than dtrans at time t equal to dtrans when in the 4th bit of the packet at host B and decide the destination. Set the speed to get across the link is faster than the three way to even get them on the fourth bit or had already reached the host. G. Was a bit difficult for me. Suppose S equal to 2.5, 10 equal to 10 to the 8th power, L equal to 128 bits, and R equal to 56K BTS. BPS, sorry. Find the distance M so that D prop equal to D trans. 5,714 meters. M equal to L divided by R times S, which transcribes to 120 bits divided by 56K BPS, then R multiplied by tracer speed, which is 2.6, 10, 8.